Okay, good morning everybody. Welcome back to our virtual school for a new term. Today we're going to start looking at some Radian work. Just before we get on to that, if there's anybody who hasn't sent their topic test through yet, can you please do so today? We are going to start marking those. Some people have already had some of those marked and returned to them, but please get those sent through today, so I don't have to chase so many of you up later in the week. We're doing Radians next. I know some people have started Radians. Some people won't have started it at all. I'm going to assume that people haven't done it. With exercises 5A and 5B, they're relatively straightforward, and I am going to miss those ones out. If you need to look at those, then feel free to have a look at them, but they are relatively trivial. And we're going to mostly be doing arc length today. So bits of the circumference of a circle, in other words. However, I will just cover the first little bit of the radian measure chapter and just talk to you about what a radian actually is, and then we'll get on to a better formula for the arc length of a circle. So a radian is a very natural measure of an angle. Degrees is very arbitrary. We randomly split a circle at excuse me, into 360 degrees. Why 360? There's no good reason. Well, I'm sure someone's got a reason somewhere, but it's not a particularly good reason, I'm sure. What we can do with radians is actually, and as probably the name suggests, the angle is linked to the radius. So if this circle has a radius r, that means that these two lengths here is r, and I'm going to tell you that also this arc length here is also r. And in this scenario where we have a radius, and I've travelled one radius along the circumference, this angle in here that is created is 1 radian. Now we normally say, so 1 radian, and there's a couple of different ways of writing this out. We either say 1 rad, and the textbook generally uses rad, or 1c is another way of writing it down. So it's like you decide to start doing a degree sign and then thought better of it halfway around. So this is just another way of measuring angles. This 1 radian is 50 odd degrees. I can never remember how much it is in terms of degrees. But the interesting thing is that if this is 1 radian, we might want to know, well, how many radians are in one circle. Excuse me. And so the best way to think about this is thinking about, okay, well, if this is, what's the circumference of any circle? Well, the circumference of any circle is 2 pi times the radius. And so far I've gone 1 radius around the circle. So if I want to do, if I times this by 2 pi r, that would take me all the way round the circle. So similarly, if I times that by 2 pi, if I times this by 2 pi, the radians by 2 pi, I'll get how much bigger that angle is to get me to 360. And indeed, 360 degrees is the same as 2 pi radians. They are equivalent to each other. So the reason why we say this is the natural measure is because it's not an arbitrary amount. It is linked with the radius of a circle and the constant pi. When you are doing integration or differentiation or any sort of calculus, degrees just don't make sense. It doesn't work. However, if you're using radians when you do calculus, when you're doing differentiation integration, then it does work. We won't go over any more of that and why it works today, but radians are a really powerful thing, and you do need to get used to using them. So given that 2 pi radians is 360 degrees, we might want to know what some other important angles are. So we've got 30 degrees, 45 degrees, 60 degrees, 90 degrees, 180 degrees, and 360 degrees. And can you guys just pause the video quickly and write down what they would be in terms of radians, and your answer should be in terms of pi. So obviously this one is 2 pi. We've already said that that's true. 2 pi rad or c. This is half as much, so this has to be just pi radians. This one's half as much, so this is pi over 2 radians. This one's half as much again, so this is pi over 4 radians. This, well, let's do this one. This one divided by 6 gives you 30. So that's pi over 6 radians. And this divided by 3 gives you 60. So that's pi over 3 radians. These are very common ones for you guys to see, and you should try and remember these ones. It's really awkward somebody suddenly saying to you, you know that thing you've been using for angle measurement for 17 years, I don't want you to use that anymore. But you really need to try and force yourself to do it. It's sort of like learning a new language. You will constantly translate in degrees to radians, probably throughout your whole A level. If you're at my stage of mathematics learning, at some point at university I stopped thinking in degrees and started thinking in radians. Heaven knows when it was. But similar to language learning, you translate in your language to the target language, and eventually you get good enough at a language to just think in the new language, which comes obviously a lot later. Okay, so there's some bits there. Can you have a quick think also? How can you go from radians to degrees? How can you convert between the two? So radians to degrees. And how can you go from degrees to radians? So in other words, what do you times by to get from one to the other? And what would you times by to get back? So have a quick think about that one, pause the video and see if you can work out what you need to multiply by. So the easiest one to use for this is this one here, because there's only pi radians, I haven't got any fraction there. So if I wanted to get from this to 180, I would need to times by 180 over pi. The pi's would cancel and I'd be left with 180. And similarly, if I want to go from degrees to radians, I need to times by pi and divide by 180. So the 180s would cancel and then I'll be left with pi. So there's a very quick crash course in radians, at least an introduction to it. There are exercises 5A and 5B, which I'm not going to set specifically today. However, if you want to do some of that independently, then feel free to do so. It just gives you a better understanding, a better fluency, I suppose, of using radians. Okay, what we're going to do now is start looking at arc length of a circle. So instead of using C for circumference, we'll also use L. Well, we don't obviously use it, but we are going to. We're going to use L as the arc length. Remember, the arc length of a circle is part of a circumference. So what I'd like you guys to do is, can you just write down what the formula is in degrees for the arc length of a circle? Think about it as a fraction of the circumference. And then afterwards, can you think about what it would be in radians? Pause the video, have a go at that. So hopefully for this one you said, okay, well, if I'm doing arc length of a circle in degrees, it's out of 360, and it will be the angle I'm using, so theta degrees times 2 pi r. You probably didn't put degrees there, which is fine. Just stick it in though now, because if you've got this in your notes, then it'll be good to see these things separately. With radians, well, I still have an angle at the centre, let's call it theta, and put a C up there. And let's not put a C, let's put rad, because it's stupid text, but right, it's rad. So theta rad, and that's out of one full revolution. One full revolution is 2 pi. And then I still times it by the same thing, because the circumference of a circle is still 2 pi r. 2 pi r doesn't think about degrees in anything, way, shape or form. So, hello Max. So this is quite a good formula, because if you think about how to simplify this slightly, the 2 pi's will cancel with each other and we're just left with theta radians times r. Or the way you'll see this mostly written is just theta r, and it will specify that theta is indeed in radians. And we can actually see that this is true from another way. We can obviously just think that this is true just from thinking about radians in general, but also we can take this first formula and see if we can convert this to an arc length.
Thought you were having a very long poo.
So one thing we can do is take this formula here and see that this actually translates straight into theta r. And the way we can do that is by rewriting this and by considering how to change from degrees into radians. So this formula here is theta degrees times 2 pi over 180 times r, and that's probably a slightly strange way of writing it. However, that's actually theta degrees times, oops, let's just say 360, shouldn't it? 360. However, that cancels down to pi over 180 times radius. And if we think back to what we did slightly earlier, how do I convert from degrees to radians? I times by pi over 180. So theta degrees times pi over 180 equals theta in radians times the radius. So you can get from one to the other, or you can just think about it from what we know about circles and fractions. Okay, so let's try an example. So here's a circle. The arc length here is 2 pi. The radius is 6, and what I want you to do is find theta. So we use our formula for arc length. L is equal to r theta. That's how it's written normally anyway, I think, in the formula booklet. The radius is 6. The arc length is 2 pi. And we don't know what the the angle is. If we rearrange this, I've got 2 pi over 6. And that cancels down to pi. Let's shut that door. Pi over 3. So a quick note on the fact that I haven't written the word rad or written a C anywhere. It is if your answer, or if the angle has got a pi in it, it is assumed that that is an angle measured in radians. So this would be assumed. I wouldn't have to write rad or C afterwards because of this pi here. The assumption is that this angle is measured in radians and not degrees. And in fact, you'll probably notice over the course of this chapter, and indeed if you carry on in your maths education, generally we don't write anything after the angle if it's measured in radians, and we do if it's measured in degrees. And you guys have always written a degree symbol for that very reason. Radians is the assumed thing that we would use as mathematicians. Degrees is something we would use in certain situations, more real life situations or things like vectors, for instance. Okay, so what I'd like you guys to do is have a go at some questions which are a bit more taxing. Well, some easier ones first, but then have a go at some more taxing ones. So exercise 5C, can you guys do question 1, 2, 5, 8 and 10? And tomorrow we'll look at a new formula for area, including radians. And then I'll get rid of this cough. Okay, have a great day, guys, and hopefully this is up in time. And if I'm not sure if the video was playing earlier when my wife suggested that my son was having a big poo, and if you heard that, I'm very sorry. Bye-bye.